Okay, thank you to be here for this tutorial, the last tutorial, because after tomorrow we have the examination. You will find after tomorrow exactly this document here. But if you look in my study, I don't know if it's exactly the same, or it could be, yeah, it could be that I put this because one student asked me about, yeah, the determinant of a matrix. But if you remember, probably this method, let me say, heuristic method, I cancel the row, I cancel the column, it's much better than to look at this equation here. If I remember well, I added this information here because one student asked me to put it. Yeah. The rest, I think, is exactly the same. This means, but the meaning of this, please don't bring this tomorrow. I mean, I am sure now, I remember. Is everything exactly the same as you can find in my study? I added this one, the determinant equation or formula, because one student asked me about it. But I don't know if it helps. It helps because it's quite abstract. If you want, we can do together. Last time we did the determinant in the context of the optimization. Now, let me recall what we did last time and we do the rest. And then we can select some chapters or topic to go in depth if we have some difficulties to understand. Again, on this, it could be that not all, let me say, elements, norm, dot product will be used. Or, moreover, sometimes I put in the text indications. This means you don't have to look at the memorandum because in the text is integrated also some indications. Believe me, you don't need to bring anything. Is everything here? Of course, you have to select. If it's not in the indication, look in this list. If you look at what we have in my study, I think the difference is this one, because one student asked me to put it. Okay, last time we have seen surjectivity, injectivity. We have seen maximum, minimum. We have seen maps, to build maps. Later, we will see if you have some question I can redo. Let me complete the rest. Basically, completing the rest means to consider, look at this memorandum. To consider easy example in terms of norms, products, linear mapping we did. Eigenvalues, eigenvectors, I think we didn't do, right? This means let me start with eigenvalues and eigenvectors because it's so difficult. Then later we are a little bit tired. We will do norms in the product, but norms in the product is just to apply the definition, believe me, more or less. It could be that there is something, but we will discuss again today, but everything we discussed during the semester. Okay, let me start with eigenvalues and eigenvector, because eigenvalue and eigenvector we can see here, basically at that. No? It could be that I improved this also. It could be that I improved, but the information were also there is also there in the memorandum, which is my style. It could be that here is a little bit more explicit. I added this sentence here. even though here I forget to put lambda here. We will do together right now. But the information is complete here. We will do. Now we will do, so we clarify also this. Okay, let me consider an exercise which we didn't do last time. Eigenvalues and eigenvector. Ja.
Ach so, okay, gut. Sollten schon absetzen.
Let me find an exercise. Here. No. Yeah, I found it. Yeah. Again, it's a shame. It could be that I will send again to Rainer. This, I don't know if this remains in LaTeX. Here should be lambda, né? A V equals lambda V. Yeah, could be, should be better if I redo, I send to Rainer, because this is an error here. Now we do the exercise, yeah. Please pay attention. Here is AV more directly, AV equals lambda V. We do the exercise now. I will correct, I will send you, I send today night to Rainer, and then he will substitute, because it could be that I generate this in LaTeX. You know LaTeX?
Yes.
We can see here, LaTeX in collaboration. It could be that sometimes, yeah, it happens to be because I'm, or the compiler. Anyway, it must be lambda. I will correct, and I will send again to Rainer. This means I cannot upload something which is not precise. But let me go together with you an exam exercise, so we clarify also this lambda. Look. Excuse me for the error, no? Let me share. I think you can see, no, somehow. I will give you a matrix. This could be the exercise for after tomorrow. I will give you a matrix. Before giving you a matrix, later, I give you a matrix. And I will ask you, please calculate the eigenvalues. You will find in the memorandum or data sheet this condition. We discussed a lot about this condition. Let me open the memorandum. So I try to clarify also this error, but after tomorrow will not with error, because I will send you again. Exactly here. The eigenvalue lambda of a matrix A are calculated as, this means apply the definition. Or, yeah, can be considered also a definition, because in a if and all if is in a theorem. This means it's there. We don't have to do, oh, this is eigenvalue. We knew, I hope that we knew a little bit the meaning, but in the exam, we don't speak about the meaning. We have to produce the results. Okay, this is correct in memorandum. We read this, and now we applied exactly this equation. Determinant of what? What is the meaning of lambda I? I is the identity matrix, I told you many times, with the corresponding dimensions. Dimension is 2 times 2. Why that? Because the matrix A is the matrix 2 times 2. In order to obtain the difference in between, two matrices must have the same dimensions. Same number of row, same number of columns. This means I don't need to specify 2 times 2 many. I don't need to specify many words. To realize the difference or the sum, algebraic sum, must be the same column, the same row. Otherwise, cannot be done. This means it's clear that I can write here lambda 0, 0, lambda minus this matrix here, which I give, equals 0. This matrix minus this matrix is easy to see because you have to subtract the corresponding element. It's intuitive. We don't need to write in the form example of the definition of the subtraction. Otherwise, I have to put the whole material of the course. What is intuitive I didn't put? Please, every question.
Minus lambda I, and you counted lambda I minus A.
Exactly. The question is very nice.
Is it A minus lambda I?
It's the same because if you multiply by minus both parts of the equation, if you remember this property that the minus in the determinant can go inside, like a distribution property, which I told you when we discussed, we introduced these 10 properties of the determinant, is the same. This means apply what I wrote in the memorandum. But if you invert, and then we repeat it, it's not an error because the determinant of lambda I minus A equal the determinant of A minus lambda I. Can be demonstrated. Isn't these 10 properties of the, let me say, of the determinant? Isn't a property? Now we have this. Now question is, should I look at the equation of the determinant, of the equation of the formula of the determinant to do that? You can do, but it's complex. When a student asked me to put, I put it. If you remember, I told you we can do in matrix 2 times 2 is extremely easy because it's easy to remember is this element multiply this element minus this element multiply this element. You can keep in mind that's the product between the diagonal element minus the product of the anti-diagonal element. It could be useful eventually, this equation, which is in the memorandum, for the determinant 3 times 3. But also this, we will see eventually later, we have seen last time, that we have also an intuitive way to cancel the line, typically the first line, but not necessarily. There is always a suitable line. Which one? The line which we have more zeros. But anyway, let me go ahead with this, then eventually we will look together. This multiply this is this. This multiply this is 0. Then Gymnasium. Lambda equal 1, lambda equal 4. We don't need to learn much. First question already done.
No. Fine.
Eigenvectors here, to calculate the eigenvectors, more directly, as I told you, I forgot lambda, but I will correct. I forgot lambda, but I will correct. This means in the data sheet, we will find not A multiply V equal V, but A multiply V equal lambda V. I will look in the LaTeX file. But now you know that there is an error, but after tomorrow will be corrected. Thanks to the memorandum. Don't trust this professor that no errors. The professor should error.
We always trust the professor.
Without error, does exist any person? No person with error. But I clarify what I will correct. Or in this form. This form, I think, is a memorandum is right. Let me see. I don't remember. But at least more directly, let me see with the glasses. Yeah. Look, is a little bit, how possible to say, behind because it's the null of this matrix, which is equivalent to say this one, if you remember the null, the kernel. But of course, probably it could be more easy for you to apply more directly, but in correct form, this, no? A multiply V equals lambda multiply V. I will do it. Exactly what I did in this lecture last semester, I don't know when. Now, what I did here, I didn't do the direct method. I apply the null matrix, or the null criterion, excuse me. I will find the vector V1 corresponding to lambda 1. This is correct. You remember, A multiply A minus lambda I. No? This is I, identity matrix. Is exactly your question. You remember, here I inverted the same. You can do it as you want. You can do this minus this, or exactly here, this minus this. Here, I inverted, probably in order to be flexible, in order to show you again during the semester that you can do as you want. It's impossible to do many mistakes, thanks to the property of the determinant. Here, I applied not the direct form, but the null form. I am looking for the null of this structure, in which this element here is lambda 1. This here. I am looking for V, which represent the null of this structure. You can write also lambda I minus A as you want. Doesn't change the null. We have also seen during the semester. I am looking for V, corresponding to lambda 1 in our case. Therefore, I put here V1, because here I have a lambda 1. If you want, I can write. This means I have to calculate V1, which consists of two parameters, A and B, A and B. This means this minus this, no problems, no? This minus this, no problems. Which multiply A and B. A and B are two parameters which characterize V1. This means row multiply column. This means 20B equals 0. Row multiply column, 3B equals 0. Did you agree? This is the two conditions from this expression. This means for both, we have a B equals 0. 3B equals 0. 20B equals 0 means B equals 0. No contradiction. This means it exists, this V1, because it seems to be, but in both conditions, I have a B equals 0. For the first product, I have a 20B equals 0. For the second product, I have a 3B equals 0. This means in both cases, B equals 0, fixed. If I have a two condition, B equal 1 and B equal 3, doesn't exist solution. Because B equal 1, B equal 3, I cannot decide. B equals 0, but very important for each A, because in these two equations or the conditions, we don't have any constraint for A. A is not mentioned. This means I have to write, very important, I have to write for each A. This condition is valid for B equals 0, but for each A, did you agree? H is not there. This means for each. Conclusion, the first eigenvector, excuse me, for the eigenvalue lambda 1 equal 1 is this one. A, which multiply 1, 0. Why 0? Because B fixed 0 from the conditions. Very important for each A. You remember, I told you the eigenvector is in a direction. This means A multiply 1, 0 states vector parallel. Do you remember the definition of parallelisms? With the vector 1, 0. Let me do now V2. I hope that I have it. Otherwise, we do together, no? But I have it. I have it.
Could we also write that the vector is A and 0? So A is pulling.
Can you write? Can you write?
And like 1 and 0 is like an example.
You can write directly here. A0, no problems. Very important, I would like to see for each A. If you forget, it's not an error that you lose credits. But very important is for each in math, you remember, quantifier like exist for each is important, right? You can choose whatever you want.
A is free choosable.
It's the same concept, the same concept. For each exactly means what you told me now. Probably if you write free choosable, this more explicit for each. Thank you for this. Yeah. Anyway, in my exam, it is difficult to make mistakes. First of all, because I ask what we did. Look, now lambda 2 is 4. I write for you here. Lambda 2 is 4. It's the same problem as before, in which I put here lambda 2 equals 4. But I'm looking for the kernel of this without this direct form. I like this. I like this. My opinion is, well, is the null, the memorandum is not written exactly this, because this, if you write, this is already the solution somehow. I put in the form the null, huh? But if you remember, the null is a subset of a transformation, the subset which is transformed into 0 in accordance with the dimension of the 0. Here the transformation which is characterized by the matrix 2 times 2 is a vector with a column vector with 2 elements. Now, from here to here is clear. I do the differences between this matrix and this matrix, considering -4 here, -4 here. And we have -3. Why that? Because 1 minus 4. We have here 20 because we have this, excuse me, we have this 0 here. Now again, 1 minus 4, we have 3 on this position. What at this position? At this position 20 because we have a 0 here, no? 20 minus 0, because 4 multiplied 0 is 0. 0 here is clear because -4 multiplies 0 again 0, 0 minus 0 is 0. Why here 0? Because we have 4 minus 4. Intuitive, the difference between two matrices. Now I have to calculate A and B, but we have seen us already. We can do. Look, row multiply column equals 0. This means -3A plus 20B equals 0. Again, row multiply column equals 0. This means from here I can write A equals 20 divided 3B for each B. Of course, you can say, but should I write in the same way B equal 3A divided 20? And for each A, yeah, it's equivalent. You can choose whatever you want. This is impossible to make mistakes. Let me assume this. But we are in the cases before, somehow, a little bit, well, different, but we can see this. A, or better to say, this condition is the unique condition, because 0 multiply A plus 0 multiply B equals 0 is automatically satisfied for each A and each B, because we have a 0 equals 0. I mean, row multiply column here does not bring information. 0 equals 0. Okay. This means it's valid for each B, for each A and each B, 0 equals 0. Here, you can choose to write in this form here for each B, or to write B equals 3 multiply A divided 20 for each A. It's equivalent. But if you choose this form here, we have V2 equal what? Please pay attention here. If you have for each B, you have in evidence B, and here we have B for each B, and here we have A, which is written here, 20 divided 3, B. You can include also B here, if you like, because probably it's more explicit because A here is inside, as you want. Before was easy because it was in a zero, but here it's not the case because it's the condition which you have between A and B. Let me see if I forgot to say something, but I don't think so. No? Or V2, as I told you before, now 1 is here, and you have a 3 divided 20 multiply A. If you choose the form B equals 3A divided 20A for each A, this means A is the parameter which can be chosen arbitrarily, to answer again your question. Ready. The question consisting of which concern eigenvalues and eigenvector should be something like that. Again, I will correct here, and I will send to Rainer for after tomorrow a lambda, but you can directly apply this. Here's a little bit, not explicit, but you should know what is zero, the null of a transformation. Means I will find a subset set V1, considering lambda 1, such that A minus lambda 1 multiply E, or the lambda 2 multiply E, everything multiply this subset characterized by A and B, in general V1 or the V2, equals 0. I think we have seen 2 or 3 exercises during the semester. This, in my opinion, this example completes this. Should I do another one, or is okay this? Should be more or less so.
I think, okay. Maybe we should do like when like how you define if the vectors are the same or diagonal. You know? Because I saw this in this memorandum.
Yeah.
I think there was also like when the vectors are the same or they are diagonal.
Which vector?
Like when you have A and then you have another vector B.
A, you intend this parameter?
Or like if the matrices are similar, sometimes we have like one vector A and then a vector B, and then we have to look if they are similar to each other.
Similar vector, you intend eigenvectors?
Yes, I think there was this formula with the P.
Okay. Let me see. Let me see the memorandum. Probably understood what you intend. Exercise related to.
But it's also related to eigenvalues and eigenvectors.
Yeah, but the similarity between matrices we didn't do. This means it could be that in my study there is this indication about the similar matrices with existing matrix P. This semester we didn't do that. This means tomorrow, after tomorrow, will not appear to evaluate the similarity of two matrices, matrix A and matrix B. Now I understand. In the past semester, sometimes it's always during the semester I did the when two matrices are similar. And in this case, I have to give you two matrices.
Yes.
But will not be the example of after, will not appear after tomorrow. Because we didn't do. Exactly. Yeah. Do you do another exercise, or should I do, or is okay? Try to do at home. You have in my study many exercises. Look for this, but this is one of these exercises which the student typically do directly because I will not put some examples in which we have a complex eigenvalues, and this means complex eigenvectors. This I will not do it because it's just complicated. I don't like to complications in calculations because it doesn't make sense.
Yeah.
Typically, then we use the computer. This means sometimes the student asks, but why we have to do this calculation if that after that the computer does everything. But we have to understand what the computer does. No? Okay. This is the topic. Linear mapping we did last time. Do you remember? Should I do another exercise or we can consider later? Let me complete. Let me complete. Now I would like to tell you something, but please tell also to the students who is not there. This exercise of pre-action is not there. To simplify the situation today in the evening and also after tomorrow. Why that? Because we did once or twice, really is not so, let me say, relevant because it's an example, an exercise inside, let me say, of the scalar product, orthogonal, and so on. Let me do in a couple of exercise on the linear combination, even though we already considered last time. Then last time we didn't do plane, hyperplane, right? Or we did? We did. We did also mapping, right?
Yes.
This means now I will do something with the linear combination. Then I will try to do some exercise on internal product between functions, even though it's not in the memorandum, but the equations are in the text of the exam. Between function in the sense when typically we say fields, when basically we have a vector of functions. We did. This is extremely easy. I show you again so you will remember what. Let me do now an exercise related to the linear combination, even though we have seen also last time. Let me reorganize here the material. And let me do this. This is an exercise that we already did last time, but in another context, on the cost of subjectivity and so on. Okay. This does not belong of the material of today. Excuse me if I spend time to reorganize here, but if I don't reorganize, I don't find the material for next time. Okay, now let me see. Something related. Okay, plane and hyperplane. We did. Okay, I have it. Oh, let me start from the beginning because I have the material here. It makes sense now. Norms, then linear combination. We conclude with internal product and so on. Look at this. Let me. So please calculate L1, L2, L infinite norms of following two vectors, V1 and V2, so defined, in which A is between 2 and 4. A is the parameter belong to R. Memorandum. Look, extremely easy here. We can find the definition of norm L1, of norm 2, norm L infinite. We have also semi-norm, but it's not in the question.
Yes.
Yeah, now I show you that you can find everything here. Now I do the solution. We have a question here. Did I understand correct that the linear mapping will not be in the exam? 9. Linear mapping will be in the exam because we did last time. You confirm. Or I forgot. We did.
Yes.
Again, linear mapping is in the exam. Don't understand. We don't do today, but at the end, if you want to do another exercise on linear map, I can do. But we consider last time. Basically, we do everything which we did during the semester. The similarity between matrices we didn't do. This means it's not there. It's not there. But linear mapping we did during the semester. And moreover, we did last time. I remember well because I have a similar course in a technical university in Poland. Yeah, which are you from Poland?
Yes.
Which town?
Wałbrzych, it's near Wrocław.
Yeah. My wife is half Polish.
Really?
Yeah.
Also,
Yeah, yeah. It's this year. I don't know if it's visible.
and where is she from?
My mother-in-law came from, the grandfather of Ellen Raczynski come from Poland.
But you don't know where exactly.
The family migrated from Poland to Ukraine for different reasons. I don't know which reason. I can ask. Yeah. We can speak later. I have the picture here. This means linear mapping is there. Don't misunderstand, because we did during the semester and we did last time. But of course, the memorandum is not exactly what we do after tomorrow. I cannot do exactly what we do until tomorrow. It could be that we have some variation, but in any case, what we will appear after tomorrow, necessarily I did during the semester. That's I guarantee it. Of course, in the memorandum, or also in this, I don't know if, and the tutorial does not cover everything, but the course cover everything which after tomorrow will appear. Linear mapping is there. Please don't do this error. No? It's there. Okay. Look at the solution. And then we have another question. Indicate for which value of A the inner product basically is the combination between norm and inner product. These two vectors equal 0. This means orthogonal. No? Of course, if A exists in this interval. Norm 1. If you look at the definition which you can find in my study also or in the memorandum, what is the norm 1? Is the sum of each component in absolute value. If you look at the, let me say in German form example, no? We have A plus 1, because this is the sum of each component in absolute value, h plus 1. Here I put again the definition, just to recall today. Norm L2. Norm L2 is known, is Euclidean norm, Pythagoras theorem. You remember this? I will not put this in the exam. Do you remember this lecture? Just to remember this lecture here. I didn't put any exercise on this topic. You remember this, no?
Yes.
The norm L1 stay a circle with this one. This is a circle. The norm L2, this is not a circle. Now I am asking you, if I move, again, don't go away, don't go away. I wait for you. This is not a circle, considering the norm LH infinite. Let me tell you about the norms, and then we will ask about this. The norm L2 is the root of the sum of the component square, Pythagoras theorem. This means a minus a squared plus 0 squared plus 1 squared. This means root of a squared plus 1. Norm L infinite, this is the definition, basically is the maximal component if I consider the component in absolute value. But you can see for the vector v1, I will consider the vector v1, that A is between 2 and 4. This means it's the maximal value of A. This means 4. And I can do the same for V2. No? I can do the same for V2. I can apply the definition. I think I sum absolute value of components. Please consider V2. No? You have to consider this. 1 plus 2 plus 1. This means 4. No meaning for the absolute value. I mean, I can do, but in accordance with the definition, but don't change anything. What about the norm 2 of V2? Root of first component square, second component plus second component square, plus third component square, Pythagoras theorem, each element square, root of 6. I can apply also the norm infinite of V2. What is the maximal value in absolute, considering absolute value? It's 2. I don't need to put absolute value. Then I do, you can do the same exercise for different vector at all. But once you did one for one vector, the rest doesn't change. The definition is there. Now, to relax a little bit the lecture, but I don't put this question. In your opinion, if I move from this point to this point within a velocity constant, I don't know, constant, 1 meter per second, no? To reach this point here, or better to say, think about atom. And then I don't answer the question. If I move on this line here, to reach this point, to reach this point, to reach this point, in your opinion, if the velocity is constant, we at a different time or the same time? I don't answer you. Think about that too. This is more interesting example. Huh? I move in a velocity, in a constant velocity, 1 meter per second, moving on this line here. How much time I need to achieve this point? How much time I need to achieve this point? How much time I need to achieve this point, in your opinion? Think about that all.
But isn't the vector only giving the direction?
The answer is related to the norm.
Mhm.
If I told you that this distance is 1, if this is 1, for instance, no? I told you that this distance is 1, this distance is 1, I will reach these 3 points at the same time.
Mhm.
It seems to be strange because it seems to be that to reach this, I need less time. But the distance is the same, in accordance with another metric, I need the same time. Now, think about this. I move along this line here to reach this point. I don't answer you. Now I don't answer you. Think about if you have the same time or not. I don't answer you. Okay. Now, it's not a question of the exam, no, just to understand that the time depends on the definition of the distance. Okay, but this is just a little bit too abstract, but we have. Okay, let me go ahead with another example that makes more sense. Okay, probably we didn't finish, no? Yeah, inner product. The inner product between V1 and V2. V1 dot V2. I copied the definition of V1 and V2. You can find in the memorandum this definition here. This means this multiplied this is minus A, 0 multiplies 2, basically 0, 1 multiply 1 is 1. This means the inner product is minus 1 minus A plus 1. It seems to be that they are orthogonal if A equal 1, right? If A equal 1. But 1 does not belong on the interval, to the interval, doesn't belong to the interval, because the interval is 2, 4. This means if A is a constraint between 2 and 4, we don't have the orthogonality. Ready? Exam exercise. Discuss the linear dependence or independence of the following vectors. Try to discuss intuitively and then analytically, this means with calculations. Look, I will give you this. In which, as before, A is a parameter which belong to R. Intuitively, in your opinion, think 1 second intuitively, and then we discuss together. Look, let me consider A not 0. Because A0 is in particular case. We discussed during the semester. But let me consider A not 0. I don't know if I put here. No, I didn't put. Oh, yeah. Or probably I told, but I didn't. Let me consider A not 0. Because if 0 is included in the set, we have to discuss a little bit. But let me consider A not 0. We have 4 vectors, V1, V2, V3, V4, in a dimension 3. This means, you remember, the number of the vector is larger than the dimension of the, in which the vectors are defined. This means I'm waiting for linear depending vectors. if A is not 0, A equals 0 in a particular case. We will discuss. I didn't write because probably we discuss. Did you agree? We have to write. Yeah, also I put some points. Intuitive. In general, 4 vectors in R up to 3, you have to write this sentence here, are necessarily dependent. Because we have 2 elements in the space, intuitively. I didn't put here any consideration about A, but please consider A is not 0. That probably is later, I don't know. A is not 0. But if A is 0, we could happen something interesting. Did you agree with this intuitive idea? Now, analytically. Look at this. Calculation in our case. Alpha 1 multiply V1 plus alpha 2 multiply V2 plus alpha 3 multiply V3 plus alpha 4 multiply V4 equals 0. Let me consider again equal A not 0. No? It's not written here, but we have to say it. Look, this is exactly explicitly, I substitute the value for lambda 1, for V1, V2, V3, V4. And then I have a very boring system, but algebraic system. But from here to here, I try to explain. Alpha 1 plus 2 times alpha 2 plus 1 multiply alpha 3 plus 0 alpha 4 equals 0. The identity principle. I add the corresponding components. I put equal to the corresponding component. 0, 0, 0, that means 0, 0, 0. And of course, what about this expression here? Alpha 1 multiply 0 plus alpha 2 multiply 0 plus alpha 3 multiply 5 plus 0 multiply alpha 4 equals 0. What about this expression here? Now, we don't need to spend words. Alpha 1 multiply 1 plus 2 times alpha 2 plus 0 multiply alpha 3 plus A multiply alpha 4. Again, A not 0. For the first equation, it seems that alpha 3 equals 0. Why that? Because this is going to 0. Yeah. No, excuse me. And if alpha 3 equals 0, why alpha 3 equals 0? I don't see it. Yeah, from here, excuse me. I forgot to comment this. From the second equation, directly I see, very often in the exam, look at the 3 equations. It seems to be extremely complex, but look, typically, in order to help you or to avoid that you spend energy in the stupid calculations, one of these, at least one of these equation, directly give very important information. Look, from this in the middle, we have directly that alpha 3 is equal to 0, because this is 0, this is 0, this is 0. 5 times alpha 3 equals 0 means alpha 3 equals 0. Clear? Ginnasio. Now, if alpha 3 equals 0 from the second equation, from the first equation, we have this expression here. Why that? Because alpha 3 is 0 now, in accordance with the second equation. Please pay attention, these 3 equations must be solved, let me say, together. This is the symbol, no? Because the linear combination must be solved together, roughly speaking. From the first equation, if this is 0, we have alpha 1 plus 2 times alpha 2 equals 0, exactly what I wrote here. This means alpha 1 equals minus 2 alpha 2. Combining this with the last equation, with this here, which we have alpha 1 plus 2 times alpha 2 plus 0 plus alpha 4 multiply r equals 0, we can see that alpha 1 plus 2 times alpha 2 is 0. This means also alpha 4 is 0. if A is not zero. Therefore, at the beginning, I told you, please pay attention. Please pay attention. A must not, must not be zero in the sense, assuming that A is not zero. Remember at the beginning, I told you. Now, it's coming back here, this condition, in this case. Because A4 is equal to 0 if A is not 0. What happens if, now we have already the solution. Because look at this. If A is not 0, alpha 4 is 0. Alpha 3 is 0. But we have a condition between alpha 1 and alpha 2. This means, again, we demonstrate analytically that these four vectors, if A is not 0, are depending. Did you agree? Because not all elements are 0. This is the definition. And I am asking you, I don't know if, but in any case, I will comment together with you, even though it's not written. What happens in your opinion if A is equal? Anyway, until here, everything is okay. But if A is not 0, what happens in your opinion? Think 1 second. If A is 0. Easy, because this expression here is satisfied for each alpha 4. We don't need to say alpha 4 equals 0. In this specific case, does not change the solution. Even in case of A equals 0, we have the dependence because the condition which stay the dependence is here. But please pay attention to this A. Because if this condition is not there, another example, if A equals 0 implies that A4 must be not 0. This means in each, please pay attention to what I am saying, case, I told you during the semester, in which the vector 0 is included in the set, we have always formally an dependence. Why that? Because the element which multiply the vector 0 not necessarily must be 0. In accordance with the definition which say that all elements must be 0 in order to have the independence. Do you remember this? But if I have a vector 0 in the set, necessarily the set is dependent. This means, please pay attention to this concept here. Okay.
So I basically, like in the first part, I tell that it's like the intuition is dependent or not, and then I just prove it in the end.
Exactly.
Okay.
But please pay attention to this parameter. If the parameter states for some value that we have a vector 0 in the set, each time which we have a vector 0 in the set, we have a set which is depending or the dependent. Why that? Because the coefficient which multiply the vector 0 for this specific A parameter not necessarily must be 0.
So when it states that the zero vector is included, it's automatically dependent.
Yeah.
Okay.
Even though it's clear it's in a particular form, why I have to include the 0 in the set. But just mathematically, in accordance with the definition, it comes from the definition. This means it happens basically discussing the value of the parameter. I don't put directly the vector 0. We take I think so, no, here. Okay, now let me share this example, which is could happen, that you can find something similar. Discuss the independence of the following set of functions with respect to A, but also to A. Because A, it could be that makes a difference. We have seen also before. Could make a difference. Could not make, but anyway, it could happen. A again is the parameter belong to A. Look at this definition. Also for functions, the definition is the same. This means we have to verify if the combination, better to say linear combination. Linear combination means that I have to multiply every function for a parameter, alpha 1, alpha 2, you can call as you want, A, B, C, and you have to sum the functions, and you have to look if to generate 0, generate means equal 0, all components, or excuse me, all parameters are 0. If all parameters are 0, we say that the functions are independent. Now, the definition is the same. The definition is in the memorandum. Should I look? No, it's there. You have seen it as in my study. No difference. Look, why directly looking at this expression, I can say that alpha 1, alpha 4, and alpha 5 equals 0. Think 10 seconds. It's easy because here I cannot find any possible combination for constant, for t up to 3, and for t up to 4, which I can find something which generates 0. I mean, here we don't have, or in any case here, but also here, any possible combination with other elements related to t up to 3, t up to 4, and the constant, we can generate 0. In order to understand better, look at this. These two elements is characterized by t. This element alpha 2 multiply t, this element is 2a alpha 3 multiply t. This means, if you consider this expression here, this must be discussed. Because look at this. If this element here inside, this parenthesis, basically this here, is equal to 0, of course, it could happen that not necessarily alpha 2 and alpha 3 are 0. We have the idea is the condition. It seems to be that you have a condition. From here, I can write this. I mean, definitively for this element, and this element must be 0, because I don't have the possibility to combine, to find conditions. But here, no, because if you put in evidence t here, we have this expression here, and equal 0, must be equal 0. This means this condition could be, must be discussed. This means alpha 2 equal minus alpha 3 multiply a. Look at this. If a is not 0, again, if a is not 0, we have this alpha 2 is equal minus alpha 3. This means in this case, if a is not 0, we have the dependence, because not all elements are 0. Please pay attention. What happens is a equals 0. If a equals 0, it's easy to discuss. If a equals 0, we have that a2 is equal to 0. Did you agree? We have, if a equals 0, we have that a2 is equal to 0, but for each a3. I am asking you, we have the dependence or the independence?
It's like with everything is 0, it's independent.
Before, we have seen A not zero, they was depending because not all element must be zero. Did you agree? Because this condition is not necessarily all must be zero. It's enough to say A2 equals minus A3 multiply A. If A is not zero, we have C. We have the dependence. Now, if A equals zero, we have A2 equals zero. But for each A3, again, we have the dependence because A alpha 3 must not be necessarily zero because it's for each A3. I don't know if this is clear.
Again, how do you know, like, from the first line that A1 and A4 and A5 are zero?
Yeah, because we don't have any possibility to combine this constant with another constant, this element with another up to 3, with element with another up to 4. I mean, to obtain zero, necessary that must be zero, that must be zero, because we cannot combine like here. We don't have conditions.
So T could
T is in a function. This means could be any values. Is this difficult?
no, maybe it's not like intuition.
Think about the definition. The independence means that all element must be zero.
Mhm. But I could also, like, I don't know how it is in English, but ausklammern the T, and then maybe I could have like A2 plus 2A3, for example, and then I could like calculate the A. And in this case, it would be dependent because it won't be zero.
You say if A is equal minus alpha 2 divided 3, if A is equal minus alpha 2 divided 3, we have this element 0. Look at this. No?
Where
But for each alpha 2 and alpha 3, did you agree? Please pay attention to what I am saying. If A, your consideration, your question is interesting. If A is equal minus alpha 2 divided alpha 3, this element is 0. This means 0 equals 0. Did you agree? But for each alpha 2 and alpha 3, this means not necessary alpha 2 and alpha 3 are 0. This means they are depending in accordance with the definition.
So for example, if I have like T A2 plus 2 TA3, then like my intuition will tell me to just put the T outside, and then I would have A2 plus 2A3, and then I would like calculate, for example, A2.
It is.
So then it would be that A3 is like I could choose it, so then it would be dependent.
Why? Because you can choose in any case. It doesn't matter which combination you are considering, you can choose something not 0. I mean, in this case here, if A is not 0, we have any condition. Think about condition. When we have a condition, in this condition, you can choose something not 0. This means something means alpha 1, alpha 2, alpha 3. This means we have the dependence. Now you can choose in a different way, A3 equals minus alpha 2 divided A, if A is not 0, of course. In this case, you can choose alpha 2, not 0. If you explicit alpha 3 in a function of alpha 2, assume that A is not 0. If f is 0 is interesting because it seems to be that alpha 2 is 0, but for each alpha 3. This means not necessarily alpha 3 must be 0. If you say for each alpha 3, this means as you told before, I can choose as I want, no? This means not necessarily 0. This means we have also the case of dependence, because not all is 0 necessarily. Your interesting question is, but if a is equal alpha 2 minus alpha 2 divided alpha 3, what happens? We have the condition is satisfied 0, but it's satisfied for each alpha 2 and each alpha 3, but of course alpha 3 not 0, huh? But this is enough to say for each alpha 2. This means not necessarily 0. When you introduce the concept for each, it's not necessarily 0. This means this says directly that we are in the case of the dependence, because the independence is characterized by all alpha in this alpha equals 0. You remember the definition?
Yes.
We can do another exercise because I see something to be considered more in depth. Let me take another one and then we do the last one. Please pay attention to this. This is more difficult. Let me.
There was also a question if we could also revise the Lagrange and the Hessian matrix again.
Yeah, we conclude these topics here.
Okay.
I do again this exercise here because I see I realize that you have others some doubts. Then we do another exercise that it could be that it will appear, and then I will answer you questions, or we can consider a particular topic. Look at this. This is more difficult, but the same concept. Dependent or independent. Definition is always the same. I will try to do a combination instead of alpha 1, alpha 2, I am considering alpha, beta, gamma. It doesn't matter. You can use also A, B, C. No? Question is, discuss if this set represents a set of functions which are depending or independent, also with respect to A. No? We have a parameter, A. I didn't put here, but A is also a real parameter. This way to write means apply the definition. Look, do you want to do alone a little bit?
It's like gamma for
T up to A,
up to A.
because I'm considering this. No?
With alpha T up to A, to alpha, no, to A.
Alpha, which multiply T up to 2A. Yeah, yeah. Directly, you can see yeah, I put yeah some consideration. Look at this. Case one. Case one. A equal 1. A equal 1. We have this expression here. This means that imply gamma equals 0 because it's the unique element in which we have t up to 1. This means I cannot find any possible combination that generate 0 not trivially for the element of related to t. But here, now, if I put in evidence as you proposed before, t up to 2, we have that necessarily alpha plus beta is equal 0, is equal 0. This means if A equal 1, the system is not independent. They are dependent because we have a relation for A equal 1, depending. Let me consider A equal 2. Why these two cases, 1 and 2? Because what is interesting here, excuse me, here, is that is fixed. Probably you cannot see. This is fixed. This means we have to consider when possible combination can be combined with this element here. And we have two possible combinations, basically. A equal 1, we already discussed, because we have these two elements that could be combined. And A equal 2. Because these two elements for A equal 2 can be combined. This means in this case B equals 0 because this element here cannot be combined with the rest. And we have alpha plus beta plus gamma equals 0, which is again depending because you have a relation. Because if alpha is minus gamma for each gamma, but in any case, we have a relation which not implies that all elements must be 0. Let me see if I can say something more.
One question.
Yeah, please.
In the last one.
Here I made mistakes. I mean, this is A, no? Excuse me.
Yeah, okay.
Excuse me, because sometimes alpha, I come from in Germany is in Gymnasium, no? But in Germany is Altsprachgymnasium. I learned Alt Greek, Alt Latin, and alpha is A, no? Yeah, this is now is correct.
So I had a question about your starting with A equals 2 line.
Yeah.
So line number 2. Yeah, and there you wrote in the calculation gamma 4t up to 4. But actually it's up to A and A equals 2, right?
Yeah.
Okay, perfect.
The error is just here, and then I calculated correctly. Did you see?
Okay, perfect.
Not exactly because I forgot 4, no? But the conclusion is the same. Excuse me for the error again. Yeah. Now, excuse me again. Now it's perfect. Did you agree? Because I put in evidence, no?
Yeah, looks good, thanks.
No, again, error. No? Let me see. No, it's not correct. No, we have error again. Let me see. Beta. Beta, das ist, right? Is alpha 0. Yeah, excuse me. We have a couple errors. Again, let me do again. Check again. Huh? We will check again when I write. Yeah, you're right. You're right. Now we will do again together. Don't write anything. Let me see now if it's. The case A equal to, this means alpha up to 4. Beta here does not change. And this 4 gamma up to 2. Now it's correct. Then we have this must be 0 because I cannot combine. This means beta plus 4 times gamma equals 0. This means this. At the end does not change the result, but there was a couple of errors. Look, if you agree with me, I don't know why the error is. Let me check here again.
Why was changed beta was alpha?
Yeah, because this is the unique t up to 4. This means necessarily this cannot be combined. To obtain 0, this must be necessarily 0 because I cannot find any combination with the rest.
But alpha equals to minus beta, which is same. Yeah.
I mean, the case number 1 is okay. Did you agree?
Okay, it's not like depending on that.
No. We have 2 separate cases.
Oh,
From home, did you agree now with these calculations? Because necessarily alpha, not beta, I don't know why the error. And then these 2 must be discussed because I can put in evidence t squared. I didn't put here t squared because what is interesting for us is the parameters. So 2. Then now beta, for instance, minus gamma multiplied 4, and then we have a relation. This means not necessarily all elements alpha, beta, gamma, also in this case are 0. Here also, this was something related to my gymnasium. A. You have 2 cases. In cases not equal, in case not equal, this and this. In this case, we have the independence. I didn't put, but it's clear from the definition. All elements must be 0 because we don't have any correlations. This is the idea. Just in these 2 cases, 1 and 2, we have a correlation. But if you don't have correlation, we don't have the dependence. Dependence means correlation. Also with words, we can understand. No? Depends with correlation. I depend on my wife because I correlate. And vice versa. Yeah, it makes sense. Independent. I didn't write, but this is the definition I told you many times. Yeah, excuse me for the confusion here. Try to do at home. Try to do at home this. Please copy.
it's both like up to 4A
A.
and 2A.
Yeah. I can ask you, what is the case which make the cases which make the difference? What about the cases which make the difference? A equal 1 to be analyzed, and A equal 1 divided 2. Now, 3 cases. Yeah, I put just 2. Also A equal 2. Yeah. No, equal 2 is wrong. A equal 1, right? Do you agree? No 2. This is correct. Oh, we have also another one. Excuse me. 3 cases. Yeah. A equal 1, A equal 1 divided 2. And A equal 1, equal 2. Did you agree with these 3 cases? We have the correlation.
But do we have to find out the cases, or will they be, will they be, no.
Now I did intuitively, but the calculation is this. You put in evidence. The idea is to put in where this come from. Put in evidence here t squared.
But like, do we have to find out that we have those two cases, like A is equal to 1 and 2 and 1 divided by 2, or like, is it written down?
You have to find.
We have to find out.
But it's not so difficult. For instance, here, no? Look at this. You can write here. Something like that. But I think the example which I will give you in the example, in the exam, it is extremely easy. We will be definitively extremely easy. Okay, the last one. The last one is here. Oh, where is lost? Yeah. Considering the following inner product between two functions. So defined. I give you in the text something like that. You have two functions, and you have the inner product defined in this form. Questions? Calculate A and B such that case number 1, 1 scalar 2t equals 0. We have here this set of functions. I forgot to say. 1 scalar 3t squared equals 0. 2t scalar 3t squared equals 0. Basically, I try all possible combination of these three functions. We have three possibilities. Case number 1, of course, if they exist. 1 multiply 2t between A and B. The integral of this from gymnasium is easy, no? 2 times t squared divided 2, this means t squared. Calculated between A and B, we have something like that. Think about the answer. When we have 0, for A equal B. Again, this is the text of the exam. You have to find A and B, because A and B characterize the inner product in accordance with the definition. This means exist because A equal B. But of course, in this case, we have a trivial solution, as is written here, because if A equal B, I annihilate the interval. This means, of course, it's not relevant, this solution, because, of course, for each function integrated between 1 is 1, 2 and 2, 3 and t, and 3, is clearly 0. This means in a trivial solution, I cannot work with this kind of sentence at the end. I would like to say that these two functions are never orthogonal, because you remember equal 0 means in the context of the inner product that the two functions or two elements, in this case two functions, are orthogonal in accordance with this definition. We have a not trivial solution, A minus B, because if A is equal minus B, nevertheless that is 0 because of square, you remember. For A equals minus B, This is 0. This is not a trivial solution. It is enough in this case to consider a symmetric interval with respect to 0. This makes sense. Huh? I mean, the interval is not 0. Let me consider the case number 2. 1 and 3t squared. I apply the definition, which I will put in the text. This means now the integral of 3 times t squared is 3 multiply t up to 3 divided 3. This means calculated between a and b. We have b up to 3 minus a up to 3. Here, we can see directly that we have just the trivial solution because necessarily must be a equal b because we have an odd exponent. A equals minus b does not work because a equals minus b means 2 times b up to 3.
I have a general. So basically, I look at the, like, if the exponent is even or odd, and then, like, when it's even, it's always like A equals to B.
A equals b is always there in this case.
Okay. But like, if it's not even, it's is A equals to minus B?
Yeah.
Because I was confused because if I have the square root, for example, it's usually equals to plus minus B. So what is correct at this point? Is it like only A equals to B, or is it A equals to plus minus B?
Very important to recognize that if A equals B is always in a trivial solution. This means this internal product cannot be used because if the integral is not defined, this is trivial because it's always 0. This means you cannot work with this. Of course, now for you, it's difficult to understand what is the meaning we cannot work. But very often in signal processing, we have exactly this concept here that we have to measure the orthogonality of signals within an interval because the signal is defined in an interval. It's not a constant value. They change over time. This means we have to consider the energy, let me say, just roughly speaking.
So it would be correct, like, if the exponent is even, to just write that A equals to B and that equals to 0. And when it's odd, just like minus B.
Yeah.
Okay. So that's a rule I can
be considered in the rule, but I would like to suggest don't keep in mind the rule, do the calculation because otherwise. Yeah.
But like,
Look at this
so I
now.
can check maybe it's like.
Look at this. Try to think about this example. The same definition. We have 6 times t up to 3 integral between a and b. This means we have 3 divided 2 at the end, which multiply b up to 4 and a up to 4. We are in the even case at the end, no? In accordance with your rule. And this means we have a both solution. One is trivial, one is not trivial. In case of even, we have both solutions. In case of odd, we have, as I told you before, this was the case, just the trivial solution. In odd, we have just the trivial solution. In case even, as in this case, we have both. The trivial solution is not interesting because works always. We cannot work with the trivial solution because we cannot distinguish, we cannot calculate how these two signals interact between. Let me see if I forgot to say something. Here the idea was a little bit to show you if you have two signals, two functions over time, we need an integral, and in particular, everything depends, very important to notice, depends on the extreme of the integration of the integral. Okay, let me see 1 second if I can tell you something. That is why I will put everything, and then I can answer a question, or I can reconsider again Lagrange. No, what's difficult was Lagrange, in your opinion. No? I lost material here. We have seen this, we have seen. This we did. I don't know if I forgot to say something, but it seems to be that I told you a lot of things. Lagrange again? Yeah? An example of Lagrange? Oh, which another question here?
Oh, I don't think so. I think like someone asked about the Lagrange.
Lagrange, okay.
Yeah.
Let me put this in inside, otherwise I lose the material. Next time. Okay, this can I put here now? Mhm. Okay, Lagrange. Let me see if I find the side of Lagrange. Lagrange. Where is Lagrange? Okay, this probably we have it. Lagrange. Where is Lagrange? Yeah, found it. Yeah, it's here. It's, we didn't do. Please pay attention. Lagrange could be a problem. I know because probably you didn't do in the math, but with the help of the memorandum, we will see this. Maxima or minima for this function here. 2x squared minus 4y squared, and the constraint y equals 2. Indication, please classify the points using bordered Hessian method. It's not a valid indication because in this semester we did just this one. In the past semester, sometimes we use another methods.
This Weierstraße.
Yeah, we didn't do.
Okay.
Oh, so.
Okay.
We didn't do. This, therefore, this semester is not a valid indication. In the other semester we did, and we did also other method, but this is the most important. No, this means
I also have a question, because when I do this apply to them,
yeah, derivative.
and then I was wondering if I have to put, like, I have the equation for x and y, and then do I have, I don't know what is in English, aber muss ich dann nach Lambda umstellen, beide?
I show you now.
Okay.
Very important, and you can see also in the memorandum. Let me see if I have. We have the Lagrange function. The memorandum. Ah, yet I closed. Stupid. In any case, in the memorandum, let me open the memorandum so we can understand better what I am telling you. Ah, I have it, the memorandum here. No. Ah, where is the memorandum? I downloaded it, or? Ah, here now. Okay. Let me share. In the memorandum on this topic here, there is everything. Look here. The gradients, the definition, but in particular now, this is interesting for us. No? The Lagrange associated to the function f x y and a constant and constraint, excuse me, g x on y. In our case, it depends just of y, but of course, in general, could be also, we have seen in the classes, both, because the plane could be also depending of not only of y, of x and so on, everything. But look here, f of x, comma y minus lambda, please pay attention, which multiply, in our case, y minus 2, no? Because this is our g. Therefore, we have this. The function minus lambda, we multiply g of xy, just in a function of y, minus 2 equals 0. This means basically this is equal 0 if you want. Is g of y, in our case, of in general x and y, minus the constant is here. Now, in accordance to your question, you have to calculate the gradient of this expression with respect to x, y, and lambda. I don't know if this was your question. X, y, and lambda, the gradient with respect to x, with respect to y, with respect to lambda.
This was clear, but the next step.
Next step. Okay, let me go ahead. If for x is clear, the derivative with respect to x, minus 8y, because the derivative, the partial derivative with respect to y, and this, the derivative with respect to lambda. This is the linear with respect to lambda. Now, if you look at the memorandum, I don't know if it's there, but it's not so difficult to remember, because if you remember in gymnasium, the maxima and the minima probably is not written. I don't remember. It's not written. Why that is not written? It's not written because from gymnasium, you have to remember that the maximum and minimum are related to the derivative, in this case, partial derivative, but equal 0. This means this must be put equal 0, this must be put equal 0, this must be put equal 0. Because if the derivative of this element with now the gradient, we replace the concept of the derivative. Why replace of the concept of the derivative? Because in our context, we don't have a function of one variable. We have a function, in particular in the Lagrange, of 3 variables, x, y, and lambda. But we are interested just in x and y. But nevertheless, we need lambda. The reason is I told you during the lecture why. This means I have to consider 3 conditions for the 3 variables of the 3 derivatives. variable in the sense this is a variable, this is another variable, this is one. This means I have to consider all trees, because the gradient, which now replaces the concept of the single derivative, the gradient isn't a partial derivative, like it's a vector, it's a partial derivative. This I didn't put in the memorandum, but I suppose that you remember that the maximum minimum is related to the derivative equals 0. In this case, it's the concept of the derivatives is more extended, because we have the gradient of the, or the vector, better to say, of the partial derivative, because you have more than one variable.
Schönen Abend. Wir schließen, Sie haben ja Schlüssel.
Yeah, yeah,
Aber wenn Sie heute bitte die Tür abschließen würden, würde ich mich freuen.
yeah, yeah, yeah.
Bei halbe Nacht nämlich offen die Tür, das ist nicht gut. Schönen Abend.
Yeah.
Ja.
This means x equals 0, y equal 2. This is interesting for us because lambda is just an help variable. This means p equals 0, 2. This is the point. Now we have to classify if this point is maximum or minimum, because as in gymnasium, the derivative equals 0 does not mean that this is enough. This is not enough to classify. We have to consider the second derivative. I don't know if you remember. In our case, we have a particular second derivative because we have an Hessian, bordered Hessian. Look. If you look at the memorandum, you have a 0 here. Here we have basically the derivative of g with respect to x, the derivative of g with respect to y, the same here. And then here inside, let me say inside on this corner, the right down corner, exactly the matrix of the second derivatives. Look at this. The derivative of g with respect to x, what is written here is a little bit let me enlarge. Yeah. Look here. The derivative of respect to x of g is 0 because, yeah, we have a y minus 2. Y minus 2 with respect to x. Let me come back. Y minus 2, the derivative with respect to x is 0 because we don't have x. We have 1 because the derivative with respect to y is 1. Also here, because this vector is equal to this one. It's easy to see, no? Why this block here? Because this element here is the second derivative of this function here with respect to x. This means I have to consider just this derivative, which is 4. The first derivative is 4x, the second derivative is 4. Why this is 8, minus 8? Because it's the second derivative of this element. Let me say the first derivative with respect to y is this one. The second derivative is minus 8. Why this is 0 and this is 0? It's 0 because this element here is the derivative of with respect to x and then with respect to y. 0. With respect to x is this one, with respect to y is 0. Why this is 0? Because here we have the derivative with respect to y and then with respect to x. This is written in the memorandum, you don't have to learn. We don't have to learn. The derivative of this with respect to x is 0, which is here. Here we have the first derivative with respect to y, which is this one, and the second, and then I have to derivate this with respect to x. Now, determinant, let me show you the determinant. Yeah, here's one of the, in any case, you can consider this, or you can consider this is the same as a line. If you fix this line, I have to calculate just with respect to this element here, because 0, 0 does not bring any calculation. I mean, -1 up to 4, why that? Because this one here is here, to be precise. No? This one here is here. But why -1 up to 4? Because we have first line, first, second, third column. This means 1 plus 3 means -1. -1 is fixed. -1 is fixed. If you look now at the memorandum, we will see up to 4 because we have I plus j. No? The position is 4 position in this sense. First row, third column. And then why this element here? Because I have to consider the minor, which remain if I eliminate this row and this column, and then the minor is the determinant of this minor, means this multiply this minus this. This is an error. I see an error here. Huh? Oh, like that. Yeah. Just -4. No? Excuse me. Just -4. Let me correct. Why just -4? Because I have to eliminate again this and this. No? This means I have to consider this minor here. This multiply this minus this multiply this. It's -4. The result does not change, but the calculation was wrong. This means -4 is instead of -32. Now, I cancel this, this is the rule. And I have to consider the determinant this minor here, this minus this multiply this, minus this multiply this, -4, excuse me for there. At the end, we have a -4 because -1 up to 4 is +1. With minus and considering the theorem, which is there now, we will look together in the memorandum. We have this is positive because M, the number of constraint, just 1. The number of constraint is just 1. This means positive. And this means, if you remember, the minimum was intuitive. Yeah, because we have a function which is going up. This is positive, is the minimum. Let me show you how you can get this information from the memorandum. This is important now, in order to sum up everything. It's here. M is the number of the constraints. We have just 1. In the exam, we have just 1. At the end, I have to evaluate this product here. Determinant was -4. And here was -1, positive, a minimum. The determinant, I put here this time, and this minus up to something is fixed. Now, the problem is to calculate the position when we are to calculate the minimum. Of course, or to calculate the determinant, excuse me. It could be that we have to consider the sum. We have to consider the sum. Could be that you have more than one element for the determinant. But I think you did a little bit this determinant in math, no? Math 2, math 1. This a little bit. Let me do this correction, and I will send again this memorandum to Rainer. The error is here, no? Lambda. Lambda. I will put now also here multiply V equals 0, no? As the null of the matrix. I mean, I will add exactly the null of the matrix. You can apply directly as today, yeah, the null of the matrix, or in the lecture, I did both. Also, this one you can use. A multiply V equal lambda V. No? I have to correct here. Okay, I think try to do this exercise, and I will put this kind of no things that we didn't do. Huh?
So if you would like upload this tutorial like today or tomorrow, so people that couldn't attend today, just like watch it tomorrow.
Okay, I will upload also on YouTube,
Okay.
also this material, but I think it's already in this, but I try to do.
No, because
But
someone
you can find in my study a lot of material. I don't know if you already.
But also, I saw also like an exercise which was about like variants and covariants and this stuff.
Yeah,
I didn't know if
it could be this semester I didn't do, but
Okay,
if you look at the presentations, you can recognize what we do, what I did, what I didn't do this semester.
okay, so it's not like relevant exercise.
As I told you, if you look again on the presentation, you can find again the exercises as
Yeah.
today, and this is the program. Of course, it could be that I copy everything, and then some past semesters we did something different. Yeah, covariance. Yeah, it could be. Yeah. Sometimes some students ask me to emphasize some part. I don't remember if I put the exam because this covariance variance statistic part does not belong directly here, but we have some connections with some topics.
Mhm.
In particular, this is related to, anyway, it's not important to clarify, but it's not variance, covariance.
Someone, I think, asked a question. Yeah.
Any question in the chat? Let me see. Recording is off now. This is way.
I think like the last one with the missing lecture.
Why does I clarify? I don't know.
I think.
We did, no?
Oh, someone answered, I think.
Lecture 6 and 7 is not in my study.
No, but someone answered that it's uploaded already.
Okay. Otherwise, I will do it. But anyway, I think I upload everything more than you need. It could be. But of course, in this whole materials, this evening, today, sometimes I can do some, I can miss some considerations, so it could happen, of course. But if you look at the whole semester tomorrow, more than the YouTube, just look at the YouTube. If you need to repeat something, look at my suggestions is look at the presentation, because in the presentation is more compact. We have nevertheless exam exercise. It could be a good recap, but if you need to see again Lagrange or specifically look at the YouTube where I did. This could be a good idea. I received a good feedback from the YouTube, even though my voice is a little bit strange, of course, without parrucca also. I would like to conclude with the recording. Eva, there's a question. Let me see.
Yes, I have a question about injectivity and surjectivity.
Yeah, please.
Could you probably fastly explain the like how you start to do them?
Yeah.
That would be great. Thank you.
Yeah, this is good idea, because also this sometimes the student have some problem in the sense, yeah, it's not so easy to, let me put, yeah, it's, and then I answer you. I do an exercise, no? One exercise for injectivity, one exercise for subjectivity.
Yes, perfect. Thanks.
what could happen after tomorrow? Let me see if I find here. Again, transformation map there. What is not there is the similarity. And of course, what is not there, the differential equation, because we didn't, I didn't consider these two topics, similarity and yeah, I have it. I have an exercise. Let me see another one. Ah, find it. Yeah. Oh, 1 second, because I found both. Yeah, let me put this. Okay. Look at this. Let me share. Let's consider this matrix here. Topic is injectivity and surjectivity. Question is, yeah, it's just an indication. We have a theorem, we discuss a lot, rank of columns equals rank of row for each matrix. I give you this matrix here. Please pay attention now. I would like that you think about 1 minute. Question is the transformation related to this matrix? Because you remember we have a map or a transformation which can be represented using matrix. I give you this and say, please discuss or say to me if this is an injective transformation or surjective transformation or both. Both means biactive transformation. No? But let me, injectivity and surjectivity. Think 30 seconds. Is injective in your opinion? And then other 30 seconds is surjective. And how I can analytically demonstrate. I don't know if you have the solution. I don't have. This means I will calculate for you. 10 seconds more to discuss the injectivity. Is not injective. Very good. Is you, in your opinion, surjective?
Yeah.
Very good. Now, the bad question. Please demonstrate.
Is it fine to say that because the rank of A has to be equal to the number of columns, and here it's not the case because it's R3 to R2, and it's not the case here, so it can't be.
Very good.
And-
I tell
But
for the students at home, and then we go ahead. Basically, you say it's not injective because the number of column, or better to say the column, are not independent. It's not a full column rank. This is the problem. If you look at the lecture, we have also a theorem. If the matrix is not full column rank, we lose the injectivity. This is the idea. And you can nevertheless demonstrate analytically calculating the kernel. You remember in the exam, if you look at the tutorial last time or during the semester, and the bad question is, please demonstrate this using the kernel. You can use two methods. you can use two methods. You can show me that the columns are depending. We did this example today also. Dependence of vectors. The columns are three vectors. Three vectors in dimension 2, nevertheless, is depending. To show them analytically, you have to consider 1, 0 multiply alpha 1, 5, 5 multiply alpha 2, 2, 1 multiply alpha t, which generate the vector 0, 0. I don't know if it's clear what I intended. Should I do it? Or you show me that the kernel is not just 0. The kernel is different to 0. This also implies that it's not injective.
Question, like if I have to show it analytically, do I have to count something, or is it okay if I just write that because of this R3 to R2, the columns are dependent, and it means that the kernel can't be only 0, or do I have to count also something? Do I have to count with the matrix there?
Typically, I ask, please demonstrate
Demonstrate, okay.
using the kernel. I will do for you.
Okay.
I mean, look, we have let me discuss the surjectivity and then I do the calculation. So it's clear what I intend. Is surjective? It's not injective, we have seen. Is surjective? When the transformation is surjective?
When the rank equals
Yeah.
to the number of rows,
Exactly.
and
Basically, when we have a row independent.
yeah, because the rank is the
What is the maximal rank in our case?
is the maximum number of linear independent rows.
Perfect. Because the minimum one. This means the range or image is exactly the codomain. Do you remember this scheme in which I put the projection, the transformation, which cover all the codomain? But this implies that the image equals the codomain. This means the rank, or better to say, the row, as you told me, are independent. Okay, let me do analytically now. Subjectivity, not injectivity. You can write, if I write intuitively, you can write this sentence. Now, analytically. To show that the map is not injective, you can use two methods, depending what I am asking you. The first method, which I don't do until the end, because we did today something similar. It's the same exercise which we did together. You have to show me that not all alpha 1, alpha 2, alpha 3 must be 0. This means the columns, they are depending. Could be done as we did today. Today we did more complicated because we have also a parameter A. We don't have a parameter A. Try to do at home that not necessarily all parameter alpha 1, alpha 2, alpha 3, must be 0 in order to guarantee this equality. This means the row are depending. We did another method, which I do now more, let me say, until I calculate completely, using the kernel of this. Two methods are equivalent. I emphasize in the lecture this one. The kernel means I would like to find, let me say in this case, x1, x2, x3. You can use any kind of nomenclature, alpha, beta, gamma, alpha 1, alpha 2, alpha 3. But now, in order to don't mix, the idea is to show you that not just the element 0, 0, 0 is mapped into 0. This was in a theory, we discussed why and so on. This means, yeah, we lose something like that. It's not exactly the best intuition, but it's not only 0 is mapped to 0. It could be that I will ask about this demonstration. But of course, it could happen this one. Why is more probably this question here? Because this question here we asked also before. Demonstrate using that the column vector are depending or independent, depends if injective or not, or not injective or is injective. Look at this. X1 plus 5x2 plus 5x3 equals 0. And then we have here 5x2 plus x3 equals 0. Not the same concept. Row multiply column, row multiply column. Did you agree with this? No? I don't know. Look at this. We have x3. It doesn't matter how you proceed. No, this is a gymnasium example, no? I think. If you put here, let me do the calculation together. We have x1 plus 5 times x2 plus or the minus 25 x2, right? Help me because I am not good in math. Eh? Right? I think, no? If I put this here, if I plug in, no? I have this one. Now, let me consider it here. We have x1 minus 20x2 equals 0. Now, we can see that x1 is equal to 20x2 for each x2. It's clear that now the null of the matrix A, think about what is the null of the matrix A? Did you agree? You can write here 20 because x1 is 20x2. Of course, you can use also alpha, beta, gamma, A, B, C. 1. What about here? Minus 5. We can see that this direction here, this means you can write also, if you forget, it's not bad, but better to put it, it's going to 0. This means it's not just 0. What about the surjectivity? Did you agree with this? No? Typically, I will ask this because this demonstration here, anyway, is already considered another example. I am sure that this can be done. This is a little bit more interesting. I clarify the meaning and so on with the nullity theorem. Do you remember the nullity theorem? Let me discuss this, the surjectivity. Why does it surjective? Because we have two independent rows. To demonstrate this, you have to write this. Please pay attention here. I like to write in column form, but you can write everything in row form. Because the sum between two rows respect the same rule of the sum of two columns. But here we have a more compact expression. But this exercise, you can do that. You will realize that, try to do at home, alpha equal beta equals 0. Did you agree? Should I do it? We can see also, but if I ask demonstrate it, this is the demonstration which we did in the exam. Basically, the dimension of the image equals the image of the codomain. I cover with the transformation associated with the matrix. Try to do at home, but we did also today. Let me see quickly. Alpha equals 0 because okay, this is beta, no? This is 5. From here we have alpha equals 0. If alpha equals 0, we have beta equals 0. Here must be satisfied. In fact, yeah, but 0 equals 0. Huh? Otherwise, we cannot speak about the dependence or independence. But it's the case. As I told you, 0 equals 0 does not bring any contradiction, and alpha and beta 0, both. This means the two rows here in column form, just formally, are independent. This means the image covers totally the codomain domain. This is a little bit here in the memorandum. Yeah, here we have the null, nullity and rank. We can see a little bit theoretically what I told you. Very important, this theorem here, which reflect theoretically exactly what I am telling you now. Huh? The dimension of V is 3. The dimension of the null is 1. The dimension of the image is this here. No? The image is 2. 3 equals 2 plus 1. Is necessary to do that? Not, but can help because I am summing up a little bit the theory related to the linear mapping. Linear mapping is there because we invested energy, time, and so on. I don't know if I answer the question related to subjectivity, injectivity, but we invested time. I think it's not a difficult. Look what is dependent, what is independent. Okay, I will stop now recording. If you have other questions, please question me. Tomorrow, it's a shame I'm not reachable because I'm traveling in South Germany. But if something happens strange during the exam, I am reachable. But believe me, do tomorrow your best. In my opinion, look at the presentations. This PDF. And then if you need to do some clarification, look at the YouTube. Now, today in the night, yeah, Sena, we are here in the night. I try to upload this material and then
Okay.
thank you really for your patience with me.